हेलो बच्चों, इस एपीसोड विच तुसी 3 डायमेंशनल ज्योमेट्री दी दोहराई करोगे। आओ हुण शुरू करिए। Coordinate axes and coordinate planes in 3-dimensional space. Consider 3 planes intersecting at a point O such that these 3 planes are mutually perpendicular to each other. These 3 planes intersect along the lines x dash OX, y dash OY and z dash OZ called the x, y and z axes respectively. We may note that these lines are mutually perpendicular to each other. These lines constitute the rectangular coordinate system. The planes XOY, YOZ and ZOX, called respectively the XY plane, YZ plane and the ZX plane, are known as the 3 coordinate planes. The 3 coordinate planes divide the space into 8 parts known as octants and denoted by first, second, third and so on up to 8th respectively. Let OA is equal to x, OB is equal to y and OC is equal to z. Then the point P will have the coordinates x, y and z and we write it as P, x, y, z. Conversely, given x, y and z, we locate the 3 points A, B and C on the 3 coordinate axes. Through the points A, B and C, we draw planes parallel to the YZ plane, ZX plane and XY plane respectively. The point of intersection of these 3 planes, namely ADPF, BDPE and CEPF, is obviously the point P corresponding to the ordered triplet X, Y, Z. We observe that if point P, whose coordinates are X, Y, Z, is any point in the space, then X, Y and Z are perpendicular distances from YZ, ZX and XY planes respectively. Distance between 2 points. Let O be the origin and let P be a point whose coordinates are x1, y1, z1 and point Q whose coordinates are x2, y2 and z2 be the 2 given points in the space. Thus, the distance between the points P and point Q is given by square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Section formula. Now come to the section formula for the point which divides a line segment into a given ratio internally or externally. Now, in the first case, when the point divides the line segment into a given ratio internally, these are x2, y2, z2 be the 2 points in space, and let R be the point on the line segment joining points P and Q such that it divides PQ internally in the ratio m1 is to m2. We can see in the figure point R is dividing the line segment PQ in the ratio m1 is to m2. Then the coordinates of the point R is given by m1 into x2 plus m2 into x1 divided by m1 plus m2, m1 into y2 plus m2 into y1 divided by m1 plus m2, m1 into z2 plus m2 into z1 divided by m1 plus m2. Now we will find the coordinates of the point R which divides the line segment PQ in the ratio m1 is to m2 externally. Let the points P whose coordinates are x1, y1, z1 and point Q whose coordinates are x2, y2, z2 be the 2 points in space, and let R be the point on the line segment PQ produced externally in the ratio m1 is to m2 where m1 is not equal to m2. Then the coordinates of the point R are given by m1 into x2 minus m2 into x1 divided by m1 minus m2, m1 into y2 minus m2 into y1 divided by m1 minus m2, m1 into z2 minus m2 into z1 divided by m1 minus m2. Midpoint and centroid of a line segment. Here, if PQ is any line segment and coordinates of point P are x1, y1, z1 and coordinates of point Q are x2, y2, z2 respectively. Since R is the midpoint of the line segment PQ, it means that m1 is equal to m2. Let it be equal to 1. So, the coordinates of midpoint R are given by x1 plus x2 divided by 2, y1 plus y2 divided by 2, z1 plus z2 divided by 2. Now, in order to find the centroid of a line segment, let x1, y1, z1, x2, y2, z2 and x3, y3, z3 be the coordinates of the vertices of a triangle. Let D be the midpoint of side BC, G be the centroid of the triangle ABC, then G divides AD in the ratio 2:1. So, the coordinates of point G are given by 1 into x1 plus 2 into x2 plus x3 by 2 divided by 1 plus 2, 1 into y1 plus 2 into y2 plus y3 by 2 divided by 1 plus 2. 1 into z1 plus 2 into z2 plus z3 by 2 divided by 1 plus 2, which is equal to x1 plus x2 plus x3 divided by 3, y1 plus y2 plus y3 divided by 3, z1 plus z2 plus z3 divided by 3. Direction cosines and direction ratios of a line. Now we will discuss about the direction cosines and direction ratios of a line. If a directed line L on a plane passing through the origin makes angles alpha, beta and gamma with x, y and z axis respectively, called the direction angles, then cosine of these angles, namely cos alpha, cos beta and cos gamma, are called the direction cosines of the directed line L. Let A, B and C be the direction ratios of a line and L, M and N be the direction cosines, that is DCs, of the line, are given by plus minus A upon square root of A square plus B square plus C square plus minus B upon square root of A square plus B square plus C square and plus minus C upon square root of A square plus B square plus C square. Direction ratio of the line segment joining two points. Let A be the point whose coordinates are x1, y1, z1 and B be the point whose coordinates are x2, y2, z2 be the 2 points. Then the direction ratios of the line segment AB are x2 minus x1, y2 minus y1 and z2 minus z1. Relation between the direction cosines of a line. Also, if L, M and N be the direction ratios of a line, then the relation among the direction ratios L, M and N is given by L square plus M square plus N square is equal to 1. Angle between two lines. Let A1, B1, C1 and A2, B2, C2 be the direction ratios of two lines and theta be the angle between them. Then the angle between the vectors R1 is equal to A1 into I cap plus B1 into J cap plus C1 into K cap and vector R2, which is equal to A2 into I cap plus B2 into J cap plus C2 into K cap, is also theta and is given by theta is equal to cos inverse A1 into A2 plus B1 into B2 plus C1 into C2 whole divided by square root of A1 square plus B1 square plus C1 square into square root of A2 square plus B2 square plus C2 square. If these two lines are perpendicular, then A1 into A2 plus B1 into B2 plus C1 into C2 is equal to 0 because cos 90 degree is equal to 0. Now let L1, M1, N1 and L2, M2, N2 be the direction cosines of two lines and theta be the angle between them. Then the angle between these lines is given by cos theta is equal to L1 into L2 plus M1 into M2 plus N1 into N2. If these two lines are perpendicular, then L1 into L2 plus M1 into M2 plus N1 into N2 is equal to 0, since cos 90 degree is equal to 0. Projection of the line segment joining 2 points on another line whose direction cosines are given. Let x1, y1, z1 and x2, y2, z2 be the coordinates of the endpoints of line segment, and L, M and N be the direction cosines of another line. Then the projection of vector AB on the line whose direction cosines are L, M and N is given by L into x2 minus x1 plus M into y2 minus y1 plus N into z2 minus z1. Equation of a straight line passing through two fixed points. Let AB be any line segment and P be any arbitrary point on this line with position vector r. Let vector A and vector B be the position vectors of 2 points through which the line passes. From the figure, we see that vector AP and vector AB are parallel. This implies that vector AB is equal to lambda times vector AP, where lambda is any arbitrary constant. This implies that vector OB minus vector OA is equal to lambda into vector OP minus vector OA, which implies that vector R minus vector A is equal to lambda into vector B minus vector A, which implies that vector R is equal to vector A plus lambda into vector B minus vector A. Cartesian form of straight line. Let the coordinates of the points through which the line passes be x1, y1, z1 and x2, y2, z2. Let P be any arbitrary point on the line with coordinates x, y, z. Then Cartesian form of straight line is given by x minus x1 divided by x2 minus x1 is equal to y minus y1 divided by y2 minus y1, which is equal to z minus z1 divided by z2 minus z1, which is the required equation of the line. Distance between two skew lines. We now determine the shortest distance between two skew lines in the following way. Let L1 and L2 be two skew lines with equations vector R is equal to vector A1 plus lambda into vector B1. Also, vector R is equal to vector A2 plus mu into vector B2. Then the shortest distance between these two skew lines is given by D is equal to mod of vector a2 minus vector a1 dot vector b1 cross vector b2 upon mod of vector b1 cross vector b2 whole mod. The point here to be noticed is that, note, if two lines intersect each other, then the shortest distance between them is 0. Distance between parallel lines. Now we will find the distance between two parallel lines. Let vector PQ be the shortest distance between the parallel lines L1 and L2, whose vector equations are vector R is equal to vector A1 plus lambda into vector B. Also, vector R is equal to vector A2 plus mu into vector B. From the figure, it is clear that vector A1 lies on line L1 and vector A2 lies on line L2. Clearly, these lines are coplanar. Then, the shortest distance between two parallel lines is given by magnitude of vector A2 minus vector A1 cross vector B divided by magnitude of vector B. Cartesian form. Let the equation of two skew lines be x minus x1 upon a1 is equal to y minus y1 upon b1 is equal to z minus z1 upon c1 and x minus x2 upon a2 is equal to y minus y2 upon b2 is equal to z minus z2 upon c2. Then the shortest distance is equal to magnitude of scalar product of vector a2 minus vector a1 and vector b1 cross vector b2 divided by magnitude of vector b1 cross vector b2, which is equal to determinant containing elements
x minus x1, y minus y1, z minus z1,
a1, b1, c1, a2, b2 and c2 divided by square root of summation of b1 into c2 minus b2 into c1 whole square. The plane. A plane is a surface such that it joins any 2 points on the surface that lies in the surface. A plane can be specified by some following given things. First one is, a plane can be specified by the normal to the plane and distance of the plane from the origin. Second is, a plane can be specified by a point on the plane and a normal to the plane. Third one is, a plane can be specified by 3 non-collinear points. And the last one is, a plane can be specified by 2 concurrent lines. Equation of plane in normal form. If vector ON is the normal from the origin to the plane and n cap is the unit vector along vector ON, then vector ON is equal to d into n cap. Let a point P whose coordinates are x, y, z be any point on the plane and vector NP is perpendicular to vector ON. Now, as here vector NP is perpendicular to vector ON and vector ON is equal to d into n cap, therefore scalar product of vector NP and vector ON is equal to 0. That is, vector np dot vector on is equal to 0. Then the equation of the plane in normal form is vector r dot unit vector n cap is equal to d. Cartesian equation of plane. Let L, M and N be the direction cosines of normal to the plane and D be the perpendicular distance of the plane from the origin. Then the equation of plane in Cartesian form is given by L into x plus M into y plus N into z is equal to D. Vector equation of a plane passing through three non-collinear points. Consider a plane such that R, S and T are three non-collinear points on it. Let us assume that position vector of point R is vector A, position vector of point S is vector B and position vector of point T is vector C. Now, as you know that points R, S and T lie on the plane, so vector RS and vector RT will also lie on the same plane. Therefore, the equation of plane passing through three non-collinear points is given by vector R minus vector A dot vector B minus vector A cross vector C minus vector A is equal to 0. Or we can say that scalar triple product of vectors vector R minus vector A, vector B minus vector A and vector C minus vector A is equal to 0. Equation of a plane in intercept form. Now we will discuss the equation of a plane in intercept form. If a plane makes intercepts of length A, B and C with x-axis, y-axis and z-axis respectively, that is, x-intercept is A, y-intercept is B and z-intercept is C, then the plane passes through the points whose coordinates are A, 0, 0, 0, B, 0 and 0, 0, C. So, x upon A plus y upon B plus z upon C is equal to 1 is the equation of the plane making intercepts of length A, B and C with x-axis, y-axis and z-axis respectively. Angle between two planes. Consider two planes intersecting each other in a straight line. If vector n1 is the normal to one plane and vector n2 is the normal to the other plane, then the planes are described by the equations vector r dot vector n1 is equal to d1 and vector r dot vector n2 is equal to d2. Let us assume that the acute angle formed between the two planes is theta. This further implies that obtuse angle between the two planes is 180 degree minus theta. Since the obtuse angle between the two planes is 180 degrees minus theta, the obtuse angle between the two lines along the planes is also 180 degrees minus theta. Now look at the quadrilateral formed by the normals vector n1, vector n2 and the intersecting lines along the two planes. Applying angle sum property of quadrilateral, you get the angles between the two normals as theta. Applying angle sum property of quadrilateral, we get the angle between the two normals as theta. The acute angle formed between the two normals is same as the acute angle formed between the planes. Similarly, obtuse angle formed between the normals vector n1 and vector n2 is same as the obtuse angle formed between the planes. Thus, we can define the angle between the two planes as the angle between their normals. Let us now calculate the angle between the two normals, which can be calculated by using the fact that dot product of vector n1 and vector n2 is equal to the product of the magnitude of vector n1, magnitude of vector n2 and cosine of angle theta. This further implies that theta is equal to cos inverse of dot product of vector n1 and vector n2 upon magnitude of vector n1 into magnitude of vector n2. The line of intersection of the planes is always perpendicular